This video is about de Broglie and Bohr. Who the heck is Bohr? Bohr had this idea of a atom. And how does de Broglie's thing go with Bohr's? Well, de Broglie's waves are an attempt to integrate why electron orbits, electron orbits, electron orbits around a proton are in distinct levels. They did some spectral analysis of a hydrogen atom, and they found out that the electrons are not a continuous form around that. In other words, as energy elevates one of the electrons, you ionize it so it goes up to a different level. You find out that that is not a continuous level. It jumps into different points. And de Broglie says, oh, I know what the problem is, or I know what the explanation is. The electrons have certain wavelengths. Remember, de Broglie says that electrons have wavelengths, or maybe you don't remember, but maybe we'll put that stuff together here in this video. And anyway, the idea is that it's like a standing wave around the proton. The wavelength of the electron is going to form different standing wave patterns from the length of the wave, or the wavelength is going to determine what the allowable allowable points are for that electron. And this will explain why Bohr's model works. This isn't the end. This is not the end by any stretch of the imagination. It's just introducing you to how things at the atomic level don't operate in a continuous mode like things happen at the macro level. Macro level is what we live in. So we have to expand our mind and accept some of these things. Okay, this should make some sense to you. Wavelength equals Planck's constant over momentum. MeV is the momentum, and this little e is the mass of an electron. Now, what are we talking about an electron for? Because we're trying to help Mr. Bohr out with some things from de Broglie, not de Broglie, de Broglie, not de Broglie, but de Broglie, and we're trying to figure out what can work with his atom model. Here's some stuff that tries to make some sense of this. Here's n wavelength equals 2 pi r. Now, what is 2 pi r? It's the circumference of a circle, 2 pi r. Anybody should know that, maybe you don't. Anyway, here's the idea, is an integral number of wavelengths must fit within the circumference of the orbit. This introduces the quantum number, which can have values 1, 2, 3, blah, so forth. So here we go. Here's MeV. That came from this setup here. MeV NH over 2 pi r. Now, does that make sense? I'll say it again. Does that make sense? maybe, maybe not. Let's go on and see if we can make some sense of it. Here, let me get the cursor. I'll get the cursor so that you can see what I'm doing. And let's see what's going on here. Okay, I did a little bit of thinking and I've got a little bit better idea how to figure out how to go from here to here. Let's bring this out and say that, let's say that V equals, what does V equal? Well, that'd be N H over 2 pi, and I'm going to put the M in there in the denominator so it matches up ME. Bring out that thing there, and then that would be R. Do you buy that? All I did is put the ME down over here. Now, we're going to go in and look at what the kinetic energy is. Okay, what did I do? I took V squared here. So look at this V squared. And notice that this over here is almost V squared. That would be 4 pi squared. But because we got the 1/2, that makes it an 8 over there. So at least we got that far. Now, what goes on next? Well, energy equals kinetic energy plus potential energy. What's the potential energy? Well, according to this write-up, the electrostatic potential energy. Let's see if we can make sense of this deal here. E is charge of an electron, and on the opposing side, the proton also has a charge equal to the electron. So these two are squared. Now let's see if we can find out some more information about this to see if we can make sense of it. Here's Coulomb's law. One charge, two charges, R squared. So the farther away from the charges you get, the force is decreased. And then there's this K. This K is the Coulomb constant. More information. Here is Coulomb constant. And we've only got an R here instead of an R squared. And I'm not quite sure where we can resolve that. But this 4 pi E0, which is the permittivity or the capacitance in a vacuum, boy, isn't that complicated. Where did I get all that information? Anyway, that's where this formula comes from. It's from two charges that are next to each other. And you can see that this electrostatic potential energy between proton and electron distance. So that's part of the evidence that I have for the electrostatic potential. This is a little confusing. I don't know if we can figure everything out here, but this is the idea that we're trying to get to. These are the allowed energies. So there's only a certain number of energies that are allowed here. And notice we've got the Planck's constant here. We've got this n, which is an integer, and this 4 pi epsilon 0, which has to do with the am I not smart enough here? 4 pi E0, that is the Coulomb's constant between these different energies. And somehow we got to this equation, and this thing right here tells us the radii that are allowed. And all those are related to an integer here, which is an n. And this apparently is supposed to show us what the Bohr atom means. Let me try to recap what all that stuff was about. De Broglie, did I say his name right? De Broglie had this idea that an electron could have waves. Bohr had an atom where apparently there were only discrete energy levels of the electrons around the hydrogen atom. Just got to start with something simple like the hydrogen atom, then we can expand it out to other atoms. But why would there only be certain levels that electron would be? Well, de Broglie had this idea that there were like standing waves around the electron, and that only those standing waves could support that model. And then what I brought out before, which I hope maybe it understood that a little bit, but the idea that the waves were actually setting it up into discrete energy levels. Does that all make sense? I think that's where I'm going to have to end this video, and then we can go on to this thing called what's his name? I can't remember his name. The guy that came up with the equation for quantum mechanics, which is, of course, everyone knows it is the Schrödinger equation, or Schrödinger. It's hard to pronounce that because it's German. It's got an umlaut over the O. So the Schrödinger equation is going to be the one that we have to focus on next. And this was just an introduction to the Schrödinger equation. So hopefully this was entertaining, even if you didn't understand any of it. But we're going to go on to the next phase of quantum mechanics that was started by this idea that de Broglie had. Hope I pronounced the French and the German guys' names correctly.